Okay, so our last question today. So before we get on that, let's just recap. So comparing series and parallel circuits. So for resistance, if you have resistors in series, the resistance increases. Again, just add them all up. If you have them in parallel, the resistance decreases. For voltage drop in series, so the sum of the voltage drop across resistors must equal to the voltage supplied. For parallel, though, the voltage drop is going to be the same for everything in parallel. For current, the current is the same in series, but we saw that the current will split at junctions, or also known as nodes. Okay. So let's scroll down and try this question together. These are the type of ones we want to be able to solve. So basically we're trying to solve this whole circuit. So we have 12 volts and we're given all these different resistors. So 200, 70, so here's our 200, 75, 50, 125, 100. So this is REQ, also known as R total, our equivalent resistance. So you see lots of these. Definitely we'll see these on quizzes and tests. So let's go about solving this one. So it's a bit more complicated than the previous ones because we have some resistors in series and some in parallel. So as you get better at this, you'll be able to do it in a single step, or just don't even have to show wouldn't have to show too much work because you just be able to see it. But I'll just break it down for this time. So I'm going to first draw my battery, my 12 volt battery. I'm just going to do one resistor at a time. And usually you want to start out as far out as possible. So I'm going to first look at R2 and R4. So you see R2 and R4, those two are in series. So I'm not going to change R1, R3, and R5 yet. Again, as you get better at these, you can kind of skip steps and do more at the same time. But R2 and R4 are going to combine, they are in series. So R1 is still 200, R3 is still 50, R5 is still 100, but 2 and 4 are in series, so 75 plus 125 is 200. Okay, so that's my first step. Then I'm going to do the next one. So you say, okay, now what can I do next? I'm going to look at the 50 and 200. So those two are in parallel. So those ones are going to combine. So R1 is still 200. I haven't touched it yet. R5 is 100. But 50 and 200 are in parallel. So go 1 over 50 plus 1 over 200. And I'm going to use to the power of -1. We get 40 ohms. So this is 40. And now you can see that those three things are in series. So we're just going to combine those. So just add them up. And we find out that 200 plus 100 plus 40, that's 340 ohms. So what we can see is that if we had a single 340 ohm, we're going to have the same current draw. So RT, our equivalent resistance, is 340 ohms. And now it's kind of like a Sudoku puzzle. You have to go step by step, kind of fill in. If you know two items, you know the third. So we can actually find out what the current drawn through the 12 volt battery. So we know that current is just voltage divided by resistance. So I'm going to go 12 volts over 340 ohms. I'm going to say 12 divided by 340, and we get a value of 0.035. Don't worry about sig figs. Just get like 3 numbers. Go with that. Usually the tools you're using are pretty precise. So let's go with like 3 numbers. So 0.0353. So I'm going to fill in 0.0353 amps. So now we have to go think about that little table we drew above. So current is the same in series. So I'm going to try to look at this one. So this battery is actually in series with R1 and R5. It's a single path. Right, so you can see there's a single possible path right now. Right, you see that? R1 and R5, it's a single wire. So the current in this thing that I just drew, that red, must be the same. So if it's 0.0353 amps to the battery, it must also be 0.0353 amps through R1. It must also be 0.0353 amps through R5. And now that we know the R and the I for those ones, we can calculate V. V equals IR. So I take 200 ohms multiplied by 0.0353. We get a value of 7.06 volts. Same thing, we have 0.0353 times 100. We get 3.53 volts. So next thing we have to recognize is, so that's a single path, but when we get to a junction, the voltage drop is the same. So what you actually want to do at this point is kind of look at your picture and say, here's a junction. Here's a junction. I know I had 12 volts right here. So that means, like, right, if I just chose a point, like right, this top left point, I know there must be 12 volts there because I gained 12 volts from the battery, but I haven't actually lost 12 volts. There's 12 volts right there. But then I'm going to lose some voltage. We know R1 is going to consume voltage. We actually just calculated that. R1 consumes 7.06 volts. It's using up 7.06 volts of our potential. So if I have 12 here and we just ate up 7.06, so 12 minus 7.06, I know there must be 4.94 volts at that location. Also, since in the circuit we know that we must use up all our potential on the other side of our battery. If I have 12 volts, I must have 0 volts. Again, doesn't matter. Here too, right there, 0 volts. Because there's no more resistors in that path until we get to the battery. So that's 0 volts there. I know R5 used up 3.53. That means there must have been 3.53 volts at this location. So now we can actually very easily solve for R3. Because we originally, so we had 12, used up 7.06, we're down to 4.94. And then we know on the other side is 3.53. So how do we go from 4.94 to 3.53? Well, we must have consumed a little bit of voltage. So 4.94, if I subtract those two numbers, we get a value of 1.41. So R3 is consuming 1.41 volts. Now I know the current. Current is voltage, so 1.41 divided by our 50 ohms. We get a value of 0.0282 amps. Now, we also, earlier we found out that the current around, like through the battery is 0.0353 amps. So I know into that junction, let's just do a little bit of erasing so you can see this a bit better. Okay. So into this junction is 0.0353 amps. And then down this path, we just found out is 0.0282 amps. The charge must be conserved. So if we add 0.0353, we know down path was 0.0282. That means in that path to the right, it's the leftover charge. 0.0071 amps. Yeah, they have to be the same because it's the same path. R2 and R4 are in series with each other, therefore the current is going to be the same. Finally, I can just solve for V. V equals IR. Multiply them together, you get 0.53 volts and 0.89 volts. Again, what we can do to check your work is just look at the different loops. So let's just erase that all again, just so you can see it. Okay, so here's one loop right here. So first we gain 12. Then we're going to lose from R1 7.06, R3 1.41, and R5 3.53. So if you add those together, V1, V3, V5, those should add up to 12. I know they add up to 12, so I'm not going to actually plug it in, but you may want to do that. Next, another path we have is right here, all the way around. So that passes through everything but R3. So if I add up V1, V2, V4, V5, those would add up to 12. Done. So it's an easy way of just checking your work.